Morning to all, and welcome to this webinar. I hope you enjoy it. The idea of this webinar is to look at different filtration types and the application and what influence the criteria in selecting different filtration. Firstly, the purpose of filtration is to prevent any solid objects entering into the irrigation system, but that is for a certain filtration grade. And the grade of filtration will be determined by the size of the objects that we need to filter or to protect the system from. As you can see there, everything is solid objects. Water treatment, so we start with the basics. We will concentrate on suspended solids today because that is what we actually take out with filtration. But there's different ways to remove suspended solids. The first one can be a hydrocyclone, or some people know it as a sand separator. Then we can use a reservoir or a dam to do sedimentation. A float suction is always a positive piece of equipment in any irrigation system because you can draw a better quality water with the float suction. Then we will get to the filtration, what we discussed today. And then something that I just want to mention that is not part of this presentation is flushing. The flushing or cleaning of your reservoir or dam, maybe at the end of the season or every second season. Your main line, your sub-main line, you need to be able to flush from time to time. And then also your laterals, if it's a micro lateral or a dripper line, you need to be able to flush it. Then also part of water treatment that we will not enter into the discussion is dissolved minerals. For greenhouses, it's quite common that we do a pre-pH treatment to neutralize carbonates or bicarbonates. And also we can do pre-easy treatment when we use either two water sources or maybe recycled rainwater that is cleaned before reuse. Things like water softening, flocculation, desalination, it's not part of today's discussion. Then lastly, we can have something like iron or manganese in the water that can create a problem, especially with dripper irrigation. For that, we need to do a process before we do filtration, and we will do oxidation. That will also be linked to the pH of the water, mixing, some contact time, settling in the dam, and then filtration. Okay. Filtration options. We basically have three different options. The first one will be pre-filtration. This is something that we need to do before we do the actual filtration. If the water quality determines that we need to do any pre-filtration. We can use a hydrocyclone, we can use sedimentation, floating suction, as was mentioned before, and then core screen. It's quite common on a canal system, or something that works also well is a rotary screen, especially on a canal system with a high algae load that we can take care of. The reason you do pre-filtration is if it's required and you don't do it, you can select a filter, but you will have, the filter will work extremely hard and it will increase your maintenance requirement and the possibility that you will have a failure during the season. Then in the primary filtration, that's the first filtration after the pre-filtration, we use basically three different types. Media, some people know that as a sand filter, but you can put different media within this filter, like glass or catalytic sand, disc filtration or screen filter. Then we have a secondary filter. This is something that we will install after the primary filtration in the field close to a valve or a group of valves, and that is to take care of anything that can accumulate in the pipeline that is small enough to pass through the primary filtration, and then they accumulate and form a group that can create, again, a problem. The important thing with secondary filtration is that the filtration grade must be the same as the primary filtration. Then the filtration selection criteria, what do we take in consideration? The filtration type, normally we will look at what we need to protect, and then we can use that as a first selection criteria. Then secondly, the water quality. That's probably one of the most important aspects. And we divide the water quality into 4 different groups or classes: good, average, poor, and extreme. And we will go into the classification in a later slide. Filtration grade, that is how fine we want to do the filtration. That will depend on the size of the orifice when we talk about the micro sprinkler or a sprinkler. And with drip, we look at the flow path. Jerry Austin had a presentation 2 days ago on dripper flow path and why it's important to look at that. The thumb rule will be normally 1/5 of the orifice. That will be our filtration grade. We will see an example on that. And also look at what the manufacturer of the products publish, what is the required filtration grade. Then the filtration area, water quality plays a big part in this selection. The system flow rate and system pressure is also important to understand. And then filter head loss, what head loss we can allow over a filter. There is norms set by SABI, our irrigation body in South Africa. And then backflush influence on the system. This is important because when we design a filtration system, we must know what is the system that we're going to protect. If it's a sugarcane project that you have extensive irrigating, say 3 to 6 hours at a time, and if you then flush for a few minutes, it will not have a big influence on the system. But if you do a greenhouse project and your irrigation is only 5-minute pulses, then you must design the filtration differently and also the pump supplying the system. Otherwise, you will have a big influence on your crop. Filter selection criteria continue. If you look at the filtration grade, I put 3 examples that's used the most commonly in the irrigation industry: 200 micron, 150 micron, and 100 micron. The 100 micron is much finer. It's double the fineness of the 200 micron. And the finer the micron is, the more filtration area I require for the same flow rate. So I can put through a 200 micron a higher flow rate than I can put through 100 micron. So if my flow rate is fixed and I determine that I need 100 micron filtration, then I must increase the filtration area to accommodate for all the criteria. The water quality, we will look at good, average, and poor for this slide. If we have a good quality water, it means that I can put a high flow rate through a certain filtration area. But as the water quality goes down to average and poor, it means that I can put less flow through the same filtration area. So the opposite again, if I have a fixed flow rate and I have my water condition, say quality as poor, then I need to increase again the filtration area compared to a good quality water. Also remember that water quality is not a fixed parameter for the whole season. It can change during the season, and we need to take that in consideration to know what happened with the water quality during the season. Velocity. Velocity is the flow rate that we pass through a certain area of the filtration area. So it's cubic meters per hour per square meter, or if you want to simplify that, meters per hour. With a screen filter, we allow a higher velocity than what we allow for a media filter. And as you can understand, the lower your velocity through the medium that you use for filtration, the more efficient the filtration will be. If you increase the velocity that it's too high for the norm that the filter is designed, then you can actually push through the dirt particles, the solid particles through the media. And you will see some examples later. There are some photos about filtration types. On the left top, you can see 2 examples of disk filtration. At the bottom left, a screen filtration. Then you will have at the bottom right, 2 examples of hydrocyclone, one from metal, the orange one, and one from plastic or polypropylene. Then on the top right, you will see an example of the media filter. In this example, the non-corrosive model. So it's not from metal. Okay, so we can compare the different filtration types. So we divide it into 3 different categories. The first one will be the filtration operation. So the media and the disk filter work on the principle of depth filtration. So if you take a sand bed, you have a sand depth of about 400 millimeters, and the water will pass from the top, move through the sand bed, and then it will go out at the bottom with special mushroom configuration. And also with the media filter, normally we put either a disk or a screen filter directly after the filter, the media filter, or the media filter bank. And that is just to prevent if there's a collapse of the underdrain, that the sand media don't pass through to the irrigation system. So if we look at separation efficiency of particles, so that's basically a lot of words just to explain how efficient the filter can catch the solid particles. And this last line will be the solid holding capacity of the filter. So that means how many of these solid particles can the filter accumulate before it builds up pressure differential high enough that the filter must be backwash. So in that criteria for filtration operation, you can see that the media filter will come out with the first prize. So it will perform the best under the filtration operation. If we look at the following backwash operation rating, then we look at the time between backflushes. So if the filter go into backflush all the different filter modules, and then in the end, the time from its finish till it builds up the pressure differential again to activate the next backflush. So the longer that time lasts, the less the filter will backflush, the better it is for the rating. The backflush water and the energy demand will be the water that you need during backflush to actually clean the filter. And the energy will be connected to the volume of water and the pressure that you need to do the backwash. So in this case, the lower the rating, the better it is for the end result or the rating. The last one is the backflush technology, the efficiency of the technology. And this is now not the filtration, but the backflush. So although the media filter have the highest efficiency for filtration, when it backflush, it's not that exciting, because you must lift the whole sand bed. And if you don't do it correctly or often enough, then you can create problems. The media filter have the highest technology in the backflush efficiency. And the reason for that is when the fully automatic disc filter that we use, the spin clean, go into backflush, we release the disc, and then we have jets of water that actually spray on the disc and then wash the disc till it's clean. And that only takes something like 20 seconds normally. So in the backflush operation, the rating, the first prize will be the disc filter with the technology that we employ there. Then there's a last category that we look at, and the first one will be what we call the failed position, and I will show you some photos on the next slide that will explain this better. Just important to remember, the disc filter will fail in a closed position, and this media and the screen will fail in an open position. So I will explain that in the next slide. The installation area or the footprint, the smaller, the better it will be. So in that case, the screen filter is normally the smallest footprint, so it gets a good point. And the media filter, because of the big design, it also needs the largest footprint. The durability of materials, it just depends if it's a material that is from steel that can corrode, or it's from a plastic or polypropylene or any non-corrosive material. So in the media and in the screen, normally they were only in steel, but today you also get them in a non-corrosive option. Then they will also be good if it's one of those models. Okay, so if we take now all three different categories, the filtration operation, the backflush operation, and the criteria that we did on this slide, the fail position, the area of installation, and the durability, if we take the sum of all of them, then you can see that the fully automatic disc filter come out tops, first prize, and then secondly the media filter, and thirdly the screen. And I'm sure there's people that can fill in this template differently, so you're welcome. This is just try to do a general assessment of the different filtration types. Okay, the fail position. If we look at the top, you will see a screen filter. The fine screen that is broken is the screen that's actually doing the filtration. The coarse screen on the outside that's still that's still operational is only there for structural support. Important to remember, a screen filter do the filtration from the inside of the screen to the outside. That means that the dirt should stay on the inside of the screen. If you look at the photo at the bottom, you will see the dirt that was pushed through the screen and is sitting on the outside where your system will actually be. This will be for two reasons. It can be that your filtration screen collapsed, like the picture on the top, or if you have too high velocity through that screen, you can also get similar results. At the bottom left, we have the media filter. This one is with a filtration sand. The way that this filter operates, normally we have an inlet with some sort of distribution mechanism to spray the water evenly over the sand at the top. The water will then pass through the sand, and the sand will then collect the dirt particles. If you can see in the front left-hand side of that picture, It's like a tunnel that's forming in the sand, and that will happen if you don't flush often enough the sand filter, that you rejuvenate the sand bed, or if you don't replace the sand when it's required, because the sand, as it over time, the sharp corners of the sand will be grinded down, and then your filtration will be different, and you need to replace it. Some cases once a season, sometimes every second season, just depending on your water quality and also the how often the filter will actually backwash, how hard the filter will work. On the top and right-hand side, the photo is from Arcal filter. That's still the Galaxy model from a few years back. There you can see the way that the disc filter work is the water, dirty water comes from the outside of the disc. Then the clean water will go through the water will go through the disc catch the particles, and the clean water will be in the inside of the disc going to the system. So there's the opposite direction that what you use for a screen filter. Now, remember I said when the disc filter fails, it fails in the closed position. You can see there, there's quite a lot of dirt accumulated on its filter. In that specific case, the filter actually clogged up completely, so there were no water that went through to the system. And this is normally when the farmer phone or the end user phone to tell you that the filter is not good. It's clogged completely. So then only when you ask the end user, but what is the purpose of the filter, that he realized that the filter is actually there to take care of the solid particles. And if that happens, the filter is actually doing its job. Maybe the water quality changed, maybe the filter was not selected correctly. There can be different reasons why it happened, but the failure is a positive failure because your irrigation system is protected in that case. That is for the English. Normally when I take a sip of water, you must know the English is getting depleted. All right, so I'm going to compare micron versus mesh, just that you know there's a difference. So if you look at the 200 micron, the yellow example, if you have 80 mesh, that will be equivalent to more or less 200 micron. It will differ slightly, but this color coding is for the specific manufacturing of the Arcal disc that we use at Netafim. We like to talk in micron, so I will go to the next slide, and you can also see why it's more it's more easy to get a feeling of the micron. A micron is 1/1000th of a millimeter. So that means if I have 100 micron, if I divide 100 by 1,000, the result will be 0.1, so it will be 0.1 millimeters. So if we look again at the yellow disc, with a 200 micron, 200 divided by 1,000 is 0.2, so that means that the opening of that disc will be 0.2 millimeters. So everything that's bigger than 0.2 millimeters will be stopped by the yellow disc. And everything that's smaller can actually pass that disc. And this is why we have the different filtration grades to adapt according to what we need to protect. If we look at the black disc, it's 100 micron, so that's basically 0.1 millimeter protection. That's double the protection that you will get on the yellow disc. So how do we link the micron or the disc color to the equipment? So firstly, if we look on the right-hand side, the green and the gray disc, we only use in industrial applications, not for the agricultural. Then, if we look at the micro, the bottom line, we say a micro we need to protect 5 times smaller than the orifice size. So if you have an orifice of 1 millimeter, And if I take 1 millimeter and I divide it by 5, I will get 0.2 of a millimeter. And 0.2 of a millimeter is 200 micron. So in that case, we use a yellow disc. So it's an easy calculation. You just need to know what is your filtration and what is your system that you need to protect. As your nozzle increase, you can go to a coarser filtration. And as the nozzle decrease in size, as you can see, if it goes below 1 millimeter, we go to a red disc. And if we go in a greenhouse with a cool net system, we will go to 100 micron. The same with drippers. The drippers, with our experience with the water quality that we have, we use either 150 or 100 micron. And the decision will be determined by the flow rate. If we have a flow rate that is 1 liter or lower per hour, then we'll go to 100 micron. And if it's higher than 1 liter, then we can go to 130 micron. Okay, so the last couple of slides, we will try to bring everything together. And for this slide, I will just explain, take more time on the first section of the slide, and then the rest we will follow. So on the left-hand side, we have the water source and the quality of the water. So the quality of the water, we can determine either by the TSS, that's the total suspended solids, either in parts per million or milligram per liter from the report from the water analyst. And for good water, we will be below 50 parts per million. Secondly, we can do what we call a clogging test that we do on site, that we can determine exactly what will be the water quality, that we do a simulation test. And as we said earlier, the water quality will change or may change over the season. So if that's the case, then we will have to do more than one test during the season and then determine the water quality. So with good water, a good example will be pumping direct from a borehole that have a steady flow of water without sand that's present in the borehole or any iron or manganese. Also, a good example will be in a greenhouse application where we collect the rainwater from the roof, and then any reservoir that is lined with a lining and a cover or a roof will also be determined as a good quality water. Obviously, it depends what we put inside that reservoir. Then in the middle, we have the equipment that we split up into 4 categories: single-use drip, multi-season drip, micro sprinklers, normally with an orifice bigger than 1 millimeter or equal, and then pivot or sprinklers. So normally pivot or sprinklers don't use any filtration as a rule, but there is cases that we can think of implementing filtration. Then the last 3 columns is the 3 different types that we want to rate or not rate, have option to select. We have the media, we have the disc and the screen. And the key for that, symbols at the bottom, if it's optional, recommended or allowed. So if we look at the single-use drip, for instance, we would recommend to go for the disc filter. The media filter is also an option to use. There's no reason not to use the media filter. And then in that case, we will allow to use a screen filter because we don't expect any problem with the water quality and the equipment that we want to protect. If we look at micro sprinklers, you can basically go for any option, but it will be either the disc or the screen that will be used in the industry the most. So that's the way that the table works. Now we will go to average water quality. You can see the criteria there for the water description and the total suspended units or the clogging time. So this is normally when we have a slow flowing rivers, streams or canals, and more in cold climates where we have a low biological growth or algae content, and that we have a proper suction, that we have settling, we take in the wind consideration connected to the suction point, and also the use of a float suction. And there you can see where the system can be used between the different media, disc or screen, and the different equipment categories. When we go to poor quality water, now we're looking at rivers and streams in hot climate. With hot climates, normally you have higher biological growth that can take place. If that happens, then normally we will do something before the filtration. It can be a fixed screen or a rotary screen or a pre-pump strainer, anything like that. Because you must also remember, between your source and your filter, we have a pump. So that biological growth or the algae can also create a big problem in your pumping, in your pump itself. Then sand, if sand is present, that also changes the factor, and I will show you in the next slide again. We will come back to the sand load. Now you can see that as the water quality reduces, then we want to increase the filter capacity and also the efficiency of the filter. We want to be use more efficient filters for that condition. Guidelines continue. This is what we call extreme. Some people call it very poor, some people call it bad. But this is water that is in a quality that you actually require pre-filtration. You cannot get away without pre-filtration. Normally when you have rivers, streams, canals affected by floods, you have a poor suction condition or you have a high sand content. So with the sand, we said on the previous slide, it's important to take care of it, because normally when you have more than 2 parts per million sand in the water, then you need to use a hydrocyclone. You cannot put too high loads of sand directly on any filter, because the filter is not designed for that. If the sand load is higher than 20 parts per million, then you cannot use a hydrocyclone anymore, but then you need to go to a settling dam. If you go to settling dams, depending on what you want to protect, if it's something like a finer material than sand that is more like silt, then we need 48 hours of settling capacity. Normally that's a good number, because if you look at the theory, you can wait a few days, but obviously the cost of your reservoir will maybe be a problem. Definitely float suction in this condition. Actually in any condition, any design, float suction is always the best option to assist you in your filtration or protecting the system. We talked about treating algae before the use on the previous slide as well, with screens or rotary screens. And then if we have high iron or manganese levels, we will take care of it before the filter as well. Because normally the iron will be not a problem, but as soon as it oxidates, then it becomes a fixed particle, and then it can create clogging for you. Or it can be food for algae to grow on, and then the two together can create a problem. So when we look at iron and manganese, we divide the source if it's from a surface water or borehole water. And you can see the criteria in parts per million when we make the decision to actually treat the water. So if we take, say, water that coming from a borehole and it is 0.5 parts per million, then we will already do a treatment. But if the water is 0.5 and it's coming from the surface, like from a river, then we will not do a treatment beforehand. And the difference there is the state of the iron. If it's already oxidated or partially oxidated, or it must still be oxidated. Like in the borehole, it's not oxidated when it leaves the borehole. So we need to make the decision earlier to do a treatment. Also important, when we do treatment of iron, for example, then we will firstly look at the pH. Sometimes we need to adjust the pH. We will add a form of oxygen that we can oxidate the water. And then we need at least 12 hours of settling in a reservoir if we want to do it in an open reservoir. And then obviously the suction point must be float suction and from the opposite side from where the water enter into the reservoir. If you look at the options now for filtration, you will see that it's either disc or media that we will use for this. And in this situation, the media filter will be your best option if you have iron, especially if you want to try and take care of the iron inline. That's not very common in South Africa, but it is possible. And the reason for the media filter is because of the slow velocity. You have a benefit in that application with the iron treatment. If we have to summarize the 3 different filtration types in general, I would say that media filter is proven as the most efficient filtration, but require a big footprint and a large volume of backflush water. The disc filter is high efficiency, precise technology, and the spin filter that's fully automatic gives you the best combination of protection, that's filtration, and backflush, cleaning the disc again. And then if you look at screen filters, because it's a single layer filter, the protection is basically limited to relative clean water and not applicable to all filtration applications. What can we take home from this presentation or webinar? We basically looked at primary and secondary filtration. So there's 3 distinct options that we can do. Sometimes we'll only have primary filtrations, and sometimes we will have a combination of the 3. Secondary filtration is something that is a very good design, especially when you have longer distance from your primary to your field. And also when you have, today we also inject fertilizer through the system. So in that case, it's also good to have secondary filters because the fertilizer can be in the line that stands food again for algae growth after the primary filter. So that's important. The system flow rate and pressure, this is something that we need to understand because it will have a very high impact on the design of the filtration. Then filtration grade, what do we need to protect? And then we will make that selection. Water quality, the most important is to understand what is the water quality that we work with and do a change during the season. And obviously we must design the system for the worst case scenario. Backflush influence on the system that we discussed. Are we allowed to influence the system during backflush or not? And that will also influence our design. Then the last 3 things, the filtration type, area, and velocity. They're all interconnected. At Netafim, we set norms for all three different types of filtration, and we follow that norms. And this norms is generated over years of experience, and it may seem sometimes conservative, but it really works. Okay, why Netafim? That's just to do some marketing, like they would say. So I'm not a marketer, so I will not use that slide, but my own words. We understand the farmer's irrigation requirement, and we can offer different irrigation systems and different filtration types. And our team at Netafim can help to select the filtration type for the different system. And the team is also equipped to support our dealer network and our farmers with the design and after-sale service. Thank you, and you're welcome to visit our Nampo Virtual stand. Thanks a lot. Baie dankie.
Thank you very much, Leon. We received a couple of questions. The first question, and there's two questions about secondary filtration, I think we can handle as one. The first one is, what determines whether you need secondary filtration or not in your drip system? Maybe you can take that one first. Okay.
Yes, it's a good question, and as we said, it's always a question of how much protection you need. So one of the people that taught me many years back, he said the water has the ability to forget that